Welcome back to another training video using the UK electrical simulator. In this video, we're going to look at different types of batteries used in off-grid solar and wind turbine systems. We'll focus on three main battery types: lead-acid, lithium iron phosphate, and sodium-ion. Lead-acid batteries are the oldest and most familiar of the three. They are still widely used because they are low-cost, widely available, and well understood. The downside is that they are heavy, have a shorter cycle life, and do not like being deeply discharged. In many systems, only around half of the battery capacity is treated as practically usable if you want a reasonable service life. So, a 300 amp-hour lead-acid battery may not really give you 300 amp-hours of regularly usable energy. You might only design around roughly 150 amp-hours, depending on the system and the manufacturer's data. Lead-acid batteries also charge more slowly towards the end of charge. They usually need proper bulk, absorption, and float charging. Flooded LED-acid batteries can also produce hydrogen gas during charging, so ventilation and correct installation are important. Whereas lithium iron phosphate, also known as LiPo or LFP batteries, is now very common in solar and off-grid battery systems. Compared with lead-acid, LFP batteries are lighter, more efficient, have a much longer cycle life, and can usually be discharged much deeper without the same level of damage. They also hold their voltage more steadily during discharge. A major advantage is that LFP is one of the safer lithium battery chemistries. It is more thermally stable than many other lithium-ion types and is widely used for home storage, off-grid systems, portable power stations, and electric vehicles. The main downside is cost. LFP batteries are normally more expensive upfront than lead-acid batteries, although over their lifetime they can work out cheaper because they last longer and provide more usable energy. LFP batteries also need a BMS, which stands for Battery Management System. The BMS protects the cells from overcharge, over-discharge, excessive current, and unsuitable temperatures. Our final battery type is sodium-ion. Sodium-ion batteries are the newer technology in this comparison. Instead of relying on lithium, they use sodium, which is more abundant and less price-sensitive than lithium. The big potential advantages are lower cost, good safety, and good performance in colder conditions. This makes sodium-ion interesting for grid storage, renewable energy systems, and lower-cost battery applications. At the moment, sodium-ion is not as common in domestic solar systems as lithium iron phosphate. LFP is still the more proven choice for many home and off-grid installations. Sodium-ion is promising, but availability, long-term field data, charger compatibility, and manufacturer support still need to catch up. So, for now, sodium-ion is a technology to watch rather than the standard choice for most current domestic off-grid systems. Pause the video here and quickly compare the three battery types before we take a look at how batteries are used and managed in the simulator. Let's open a saved workspace showing a previous setup, but this time with additional batteries. In the simulator, we currently use lithium-style battery storage, with 3 voltage options to choose from: 12 volts, 24 volts, or 48 volts. Depending on the size of the inverter and the amount of stored energy required, you may need to add several batteries in parallel. This is possible in the simulator because the charge controller and inverter charger can handle this arrangement. We simply add positive and negative connectors and wire the batteries in parallel. On the workspace, we have the familiar 6 solar panels, a solar charge controller, an inverter charger, and a 3 kilowatt load. However, we now have 3 batteries, all wired in parallel. If we switch on the charge controller, we can see it charging in bulk mode, with around 20 amps of charging current split between the 3 batteries. If we move the sun slider to 100%, the current rises to almost 40 amps, with roughly 13 amps going into each battery. In the simulator, each battery has a built-in battery management system, and the batteries communicate with each other. If one battery is at a different state of charge, the system can reduce or throttle the current into that battery as it gets closer to full charge, helping all 3 batteries reach 100% together. We can see this by using the manual battery slider on each battery and setting each one to a different state of charge. Each battery then shows a different current value. With a modern BMS and compatible equipment, This type of current management can also happen in real systems. We are now in float mode, with minimal current flow. Let's switch on the load and activate the inverter charger, then watch the batteries start to discharge. We can see current from each battery combining to provide the inverter with almost 60 amps of total DC current. Once the batteries drop below the set return value, such as 97% state of charge, the solar charge controller starts charging the batteries again. However, the 3 kilowatt load is still drawing power. If the solar panels cannot provide enough energy to cover the load and recharge the batteries will continue to drain. If they eventually reach the low cutoff point, which is set to around 10% in the simulator, the inverter charger will stop inverting and move into an idle state to protect the batteries. Once the batteries have recharged to the restart level, the inverter can start again and the process continues. I hope you've enjoyed this video looking at different battery technologies and how lithium-style batteries are used in the simulator. In the next video, we'll spend some time looking at the inverter charger in more detail, and we'll also add a generator to the system. Please like, subscribe, and leave a comment below.